Hello students. In our last class we discussed about the electrical and magnetic properties of solid, and in magnetic properties of solid we have seen what is paramagnetism, what is diamagnetism. Then after that we have seen what is ferrimagnetism, and the last topic that we discussed was antiferromagnetic substances. And the fifth magnetic properties we have got is ferrimagnetism. Okay. It is observed when the magnetic moments of the domains in the substance are aligned in parallel and anti-parallel direction in unequal numbers. Say for example, if you see this one, okay, this is the alignment of the domains. So over here you can see these two alignments are parallel with this one, and this is unequal in number. That means these two are parallel with this one, but this is 1 1. You can see 2, and over here 1 1. So they are weakly attracted by magnetic field as compared to ferromagnetic substance. For example, Fe3O4, MgFe2O4, ZnFe2O4, these substances also lose ferromagnetism on heating and became paramagnetic. This is ferrimagnetic. Now over here we have got a temperature known as Curie temperature. Okay, let us see. All ferromagnetic and antiferromagnetic solids change to the paramagnetic state at a particular temperature due to randomization of spins. Example, Fe3O4 becomes paramagnetic when heated to 577 degrees Celsius. Each ferromagnetic substance has a characteristic temperature above which no ferromagnetism is observed. This temperature is known as Curie temperature. So at this temperature, the all ferromagnetic and antiferromagnetic change to paramagnetic state. Next we have got dielectric properties. Dielectric properties means a substance to which there is no flow of electric charge when placed under an applied electric field is known as dielectrical material. Over here we need to know about piezoelectricity. What is it? So the crystals in which dipoles may align themselves in an ordered way to give some net dipoles are called piezoelectric crystals. Such type of crystals, when subjected to pressure or mechanical stress, produce electricity called piezoelectricity. Example, quartz, rochelle salt, ammonium dihydrogen phosphate, lead zirconate. Okay, all these are examples of piezoelectricity substances. And pyroelectricity means some of the polar crystals when heated produce a small amount of electric current. The electricity produced is called pyroelectricity. Next we need to discuss about types of crystals. So we have got basically three types of crystals. We have to see one by one. So the first crystal is ionic crystal. So the example of ionic crystals you can find in sodium chloride, or we call rock salt. Okay, in this crystal the chloride ions adopt a cubic closed packed arrangement. Therefore chloride ions are present at all the corners and at the center of each face. Therefore they have a face centered arrangement. So in sodium chloride crystal they have got FCC structure, we can say. Sodium ions occupy the octahedral sites. They are present at the edge center and the body center. This arrangement is called body centered. Now, each sodium ions is surrounded by 6 chloride ion, and each chloride ion is surrounded by 6 sodium ion. Therefore, the coordination number of each sodium and chloride ion is 6. Whereas number of sodium and chloride ions present per unit cell comes to 4. So unit cell of sodium chloride has 4 sodium and 4 chloride ions. These ions are held by strong electrostatic force of attraction. Sodium ions are arranged octahedral around each chloride ion, and in solid state these ions are not free to move. Thus sodium chloride does not conduct electricity in solid state. It conducts electricity only in liquid or molten state, we can say. So this is the structure of sodium chloride crystals that we have explained right now. Next we have got Metallic crystal, the second type of crystals. So the first one is ionic crystal, the second type is metallic crystals. The example we have got copper crystal. Silent features of copper crystals. Copper has CCC, that means cubic close packed structure, and it has a face centered arrangement, as we have got for sodium chloride. The coordination number of copper ion is 12. Out of this 12 copper ions, 6 ions are present in one plane, while 3 are below the plane and 3 are above the plane. The total number of copper ions present per unit cell is 4. These ions are held by metallic bond. So that is about the second type of crystals, that is metallic crystals. And you can see the diagram over here for the copper crystals. And the third type we have got is atomic or covalent crystals. So, and the good example for this is diamond. The unit cell of diamond crystal is a regular tetrahedral having one carbon atom at each of its 4 corners and one carbon atom lying at its center. In this unit cell, the central carbon atom is linked to the corner atoms by a covalent bond. So they are linked with each other by a covalent bond. Two such unit cell joined by covalent bond to form closed packed lattice. Therefore, the coordination number of carbon in diamond is 4. Each carbon atom is sp3 hybridized and the bond angle is 109.28 minutes. The carbon atoms are linked to each other by strong sigma bond which are formed as a result of sp3 overlap, and diamond crystallizes in FCC structure. The structure of diamond can be used to explain some of the properties of diamond. Number 1 is high density. Since carbon-carbon bond length is very small, that is 1.54 Armstrong, the carbon atoms are packed very close to each other and therefore mass per unit volume is high. Whereas number 2, diamond is a non-conductor of electricity since all the valence electrons are involved in bonding and no free electron is left. And the third one is diamond is extremely hard and has a high melting point. This is due to the fact that diamond crystals consist of a large number of carbon-carbon covalent bonds, which have very high bond energy. Large amount of energy is required to break these bonds. Since the bond length is small, carbon atoms are present very close to each other, making diamond hard. So the hardness of the diamond comes from the covalent bonds and the large amount of energy that is required to break it. And the last point we have got for it is diamond has a great brilliance. That means it has got a good shining property, you can say. The refractive index of diamond is 2.75, which is higher than any other solid. Due to octahedral structure comprises of 2 prisms joined base to base, such arrangement causes total internal reflection of light. So the diamond is cut in such a way so that a total internal reflection phenomenon takes place. This is the reason why there is extraordinary brilliance of diamond. So